At 124 light-years away, James Webb saw a chemical pattern linked to life on Earth. But when other scientists reopened the data, the most important part of that pattern began to disappear. The same planet went from a possible ocean world with a biological gas to a lesson in how easily noise can look like life. And the reason is hidden inside a few pixels of starlight. The planet is K2-18b. It circles a cool red dwarf in Leo every 33 days. Its mass is about 8.5 Earths, its radius about 2.5 Earths, and it sits in the star's habitable zone. That last phrase sounds more Earth-like than it is. It only means the planet receives an amount of energy compatible with liquid water under the right conditions. It says nothing about a breathable atmosphere, a solid surface, or an ocean. K2-18b belongs to a class absent from our solar system, sub-Neptunes. These worlds are larger than rocky planets and smaller than Neptune. They are also common. Some can carry deep hydrogen envelopes over hot interiors. Others can hold enormous amounts of water. A third model, proposed in 2021, describes a Hycean world, a global ocean beneath a hydrogen-rich sky. That possibility made K2-18b unusually valuable. A hydrogen atmosphere expands far above a planet, so more starlight passes through it during a transit. Each gas removes particular wavelengths. Webb never photographs an alien sea. It measures how much light is missing while the planet crosses its star. Then, researchers compare that spectrum with thousands of atmospheric models. The scale of that measurement is the first reason caution matters. The atmosphere changes the brightness of the star by a fraction of a percent, while the telescope, the star, and the detector all add their own patterns. Webb watches several transits, calibrates millions of detector values, and combines them into a spectrum. The final graph looks clean because an enormous chain of corrections has already happened before any molecule is named. In 2023, Webb's near-infrared instruments produced the most detailed spectrum yet of a habitable zone sub-Neptune. The original analysis reported methane at 5 sigma confidence and carbon dioxide at 3 sigma. Both gases fit a hydrogen-rich atmosphere. Combined with little detected ammonia, they also fit the chemistry expected above a water ocean. But here's the first turn in the investigation. A spectrum does not identify a landscape. The same methane-rich pattern can also emerge from a mini-Neptune with no accessible ocean at all. Webb had established a carbon-rich atmosphere. It had not established a habitable surface. Then, one weak feature changed the entire story. The 2023 spectrum contained a tentative preference for dimethyl sulfide, or DMS. In Earth's atmosphere, most DMS comes from marine microorganisms. That made it an obvious biosignature candidate. Not proof of life, but a gas whose abundance could demand a biological explanation after non-biological sources were eliminated. The feature was weak. The team said so. Webb needed a different instrument, working in the mid-infrared, to test it. In 2025, those MIRI observations arrived. The new spectrum was not flat, and one analysis found that DMS, dimethyl disulfide, or a mixture of both, gave the best explanation among the molecules tested. The reported preference was around 3 sigma. That phrase crossed the internet as a 99.7% chance of life. It means nothing of the sort. 3 sigma describes how surprising a pattern would be under a specific noise model. It does not measure the probability that aliens exist, that K2-18b has an ocean, or even that DMS is the correct molecule. Change the instrument systematics, the wavelength bins, or the list of gases allowed in the model, and the answer can change. Atmospheric retrieval is a competition among explanations. A computer generates spectra for different temperatures, cloud layers, and chemical mixtures, then scores how well each family matches the observations. If the candidate list excludes a molecule with a similar signature, DMS can win by default.
If the noise is treated as perfectly random when it contains a repeating instrumental pattern, the confidence can inflate.
The output is only as complete as the physical possibilities and detector behavior placed into the calculation. And this is where the signal becomes more interesting than the headline. DMS and DMDS do not leave one clean barcode. Their absorption overlaps with other hydrocarbons. Ethane, ethylene, and additional methyl-bearing molecules can imitate parts of the same broad shape. The laboratory measurements used to calculate some of these signatures are also less complete at the temperatures and pressures relevant to K2-18b. There is a second problem. A gas associated with biology on modern Earth does not remain exclusively biological on every planet. DMS has been measured in material from Comet 67P. Photochemical models published with newer K2-18b data show that sulfur-bearing gases can form without organisms in massive hydrogen-rich atmospheres. Before a molecule becomes evidence for life, researchers must demonstrate that the planet itself cannot make it through geology, atmospheric chemistry, impacts, or stellar radiation. The MIRI result did not clear that bar. It did not even establish which molecule produced the shape. It established that one reduction of a difficult spectrum preferred a family of candidate gases. But that's not the most damaging part. Independent teams did not need a new telescope to challenge the claim. They used the same Webb observations. One group combined the near and mid-infrared spectrum, processed the data through 3 reduction pipelines, and tested it with 2 retrieval frameworks. Their conclusion was direct: insufficient evidence for DMS or DMDS. Models containing ethane fit equally well. Small changes in reduction altered the preferred answer. Their estimate was brutal. Roughly 25 additional MIRI transits would be required just to reject a flat line at 3 sigma for the proposed feature. The signal had not become stronger. The uncertainty had become visible. Another independent study attacked an even earlier layer of the problem: the pixels coming from MIRI. Its authors found that unresolved instrumental systematics and wavelength binning could generate a wide assortment of planet spectra. Using their favored binning, 87.5% of retrievals did not recover the proposed DMS or DMDS signal. Across the full spectrum, they found no statistically significant evidence for a biosignature. The question is then unavoidable. Did Webb see a molecule, or did a data processing choice create a molecule-shaped shadow? This is not evidence that anyone manipulated the result. It is how frontier astronomy works. K2-18b's atmosphere blocks only a tiny additional fraction of its star's light. Researchers calibrate detector behavior, remove stellar and instrumental effects, group wavelengths into bins, and compare the remainder against models containing many overlapping gases. Every defensible choice carries assumptions. A real signal should survive those choices. That survival test is why independent reduction matters more than a dramatic first paper. Different groups write different software, choose different calibration steps, and allow different molecules into the retrieval. Agreement across those routes is powerful because the shared answer no longer depends on one chain of decisions. Disagreement is equally valuable. It reveals exactly where the claimed certainty entered the analysis. The DMS claim has not. At the same time, the planet did not become boring. 4 additional near-spec transits reported in 2025 strengthened the detections of methane and carbon dioxide and supported a water-rich interior. The same work found only marginal sulfur gas preferences, all below 3 sigma under broad model choices. A 2026 photochemical study then showed that a Hycean ocean model can reproduce the near-infrared spectrum without invoking DMS. Mini-Neptune models remain viable too, and yet this is the part almost nobody tells you. Those competing models are the discovery. We are looking at a type of world that our solar system never gave us. K2-18b can be consistent with a deep ocean under a thin hydrogen atmosphere, or with a gas-rich planet hiding water far below, pressures no organism could tolerate. The atmosphere is real. The ocean remains unconfirmed. The life signal is absent at statistical significance. That hierarchy matters. Methane is the strongest detection. Carbon dioxide is supported by newer data, though its inferred abundance depends on the analysis.
A water-rich interior is favored by some models. DMS and DMDS remain unsupported as biosignatures. 4 sentences, 4 different confidence levels. A headline compresses them into one. Webb did exactly what it was built to do. It turned a point of light into a chemical argument across 124 light years. The failure was expecting one disputed feature to finish that argument.
A credible claim of life will need repeated transits, independent reductions, laboratory spectra, atmospheric models that exclude non-biological chemistry, and several gases that make sense together.
It will also need context. A biological gas cannot be judged apart from the star's ultraviolet radiation, the planet's temperature, the depth of its hydrogen envelope, and the other molecules present. Methane beside oxygen on a rocky world tells a different chemical story from methane inside a massive hydrogen atmosphere. Biosignatures are not magic words in a spectrum.
They are imbalances that a complete planetary system struggles to maintain without biology. Here is the unsettling conclusion. The first convincing evidence of alien life will not arrive as one perfect signal. It will arrive as a result that survives every attempt to make it disappear. K218b has already survived as an extraordinary planet. Its proposed biosignature has not. The opening pattern did not reveal life. It revealed how difficult recognizing life from this far away will be. Next, astronomers mapped something that cannot emit, absorb, or reflect light, and the map exposed a structure we still cannot explain.